All right, this is the second video in our curve sketching section, and today we are going to sketch a rational function. Okay, a rational function because it's in the form of a fraction. The first video we did, we looked at a polynomial function. Okay, so the polynomial function was f of x equals x to the fourth minus 4x cubed. All right, that was the polynomial example we did in the first video. Today we're going to look at a rational function. Now to save some time, all right, this is the function we're going to sketch. I've calculated the first derivative, which I will need for the intervals of increase and decrease. So I did a quotient rule, there's the work. And I found the second derivative. So I took the derivative of this, another quotient rule, but this time I combined quotient and chain. And there is the work. Feel free to pause it. This is the work for the following. So my second derivative is equal to 2 times 1 plus 3x squared over 1 minus x squared to the power of 3. And I wrote those two derivatives right here. Okay? You can also see this in your Teams page. This file has been attached. So for starters, I want to find the intercepts. So to find the x-intercepts, I'm going to take the original function so f of x equals x squared over 1 minus x squared. And what I'm going to do is I'm going to replace the f of x with a 0. So I've got 0 equals x squared divided by 1 minus x squared. Now to solve this, remember this is like 0 over 1. So I can cross multiply. I'd have 0 times 1 minus x squared. That would give me 0. And I would have x squared times 1. That would give me x squared equal to 0. All right, or you can think of it as multiplying both the right-hand side by 1 minus x squared and the left-hand side by 1 minus x squared, and you would be left with this. Take the square root of both sides, and you would have x equals 0. Okay, that means my x-intercept is x is 0 and y is 0. 0, comma 0. Y-intercept's going to work out to be the same thing, but here's the math to prove it. F of x equals x squared over 1 minus x squared. This time I'm replacing the x's with zeros. So fill a 0 in everywhere you see an x, and you end up with f at 0 equal to 0 over 1. Okay, 0 squared is 0. 1 minus 0 gives you 1. F at 0 is 0. That point is the same as this point. So the x and y intercept are both at the origin. Next thing I want to do is, so I can check this off the list, is to find the symmetry. And remember from our previous video, the test for symmetry is to take your f of x equation and you're going to replace all of the x's with a negative x. And when I work this out, I got f at negative x equal to negative x times negative x is positive x squared. Negative x times negative x, again, is positive x squared multiplied by this negative would give you negative x squared. Now you might notice something. You might notice that f at negative x, this thing right here, is exactly the same as f of x. So we can say f at negative x equals f of x. That means the function is even. And if it's even, it is symmetric about the y-axis. So you could draw everything to the right of the y-axis and then just flip it across. It's a way to shorten up the sketching part. I actually usually just do it right from the get-go anyways, but you'll see once I have it drawn what I mean by it's symmetric about the y-axis. Now, if f at negative x was equal to negative x squared over 1 minus x squared, or f at negative x, we'd say it's odd and it's symmetric about the origin. Okay, now we're going to move on to asymptotes. So the asymptotes, will start with the vertical asymptote, that is the zeros of the denominator. So I'm going to use my original function again, and I'm going to take the denominator, and I'm going to set it equal to 0. So the denominator in this case is 1 minus x squared. All right, a couple ways I can solve this. I can factor it, or probably easiest to just move the negative x squared from the left to the right to make it a positive x squared, and then take the square root of it. But remember, when you take the square root of 1, you could get plus or minus 1. So that means there are two vertical asymptotes, one at positive 1 and one at negative 1. So that means I would go to positive 1 or 1 unit to the right, and I'll draw a vertical dashed line when I start making my sketch, and I'll go 1 unit to the left, and I'll draw a vertical dashed line when I start making my sketch. I also need to, I'll put a little star beside this, check behavior of the function to the left and right of the vertical asymptote. And I'll do that next, or on the next page when I go to make my sketch. Okay, so I'll put a little reminder here. I'll do that on the next page. I have it set up and ready to go. The horizontal asymptote. Again, we use the original function. What I want to do here is I want to evaluate the limit as x approaches infinity of x squared over 1 minus x squared. Now the move, okay, some textbooks will say divide everything by the highest degree. Others will say divide everything by the highest degree in the denominator. It's all good, okay? In this case, it wouldn't matter because the highest degree is x squared. So I'm going to divide the numerator and the denominator by x squared. That would give me the limit as x approaches infinity. X squared divided by x squared is 1. This piece doesn't simplify. 1 over x squared minus 1. Okay, x squared divided by x squared. Now, think about this. If x is approaching infinity, what would be happening to this term right here in the denominator? Well, 1 divided by a really, really large number squared, okay, this piece is actually going to get closer and closer to 0. It's going to go away. So what I'm going to be left with is 1 divided by 0 minus 1, which is 1 over negative 1, which is equal to negative 1. My horizontal asymptote, okay, would be at y equals negative 1. So that's where my horizontal asymptote is. That means I would go down 1 unit and draw a horizontal line. Over here, I have two vertical asymptotes, one at x equal to 1 and one at x equal to negative 1. So vertical asymptotes are the zeros of the denominator. Horizontal asymptote, we're calculating the limit as x approaches infinity of the original function. And by a similar process, if I approach negative infinity, I'd also get negative 1 as well. There's only one horizontal asymptote in this question. What that means is if I move to the extreme right, as my x values get really, really large, my y values get closer to negative 1. Same thing if I move to the extreme left, if I approach negative infinity, my x values get really small, my y values get closer to negative 1. All right, so now I want to find the intervals of increase and decrease. And in order to do that, just like my polynomial function, I have to use the first derivative. Okay, I'm going to be working with this. So f prime x equals 2x over 1 minus x squared, all to the power of 2. Okay, what I need to do is I need to find my critical values. To do that, I am going to take the numerator, 2x, and I'll set it equal to 0. And I'm also going to take the denominator, 1 minus x squared to the power of 2, and I'll set it equal to 0. Because, keep in mind that critical values are the values of x that not only make this the derivative 0, so whatever makes the numerator 0 would make this whole thing 0, but also are the values of x that make the first derivative undefined. So anything that makes the denominator 0 would also be a critical value. My critical numbers, if I divide by 2, I get x equals 0. Here I'll take the square root of both sides. I'll add x squared to both sides, and then I'll take the square root of both sides. So the square root of x squared would be x, the square root of 1 is plus or minus 1. Don't forget, a common mistake is students just write positive 1. So these are my critical values. I've got x equal to -1, 0, and positive 1. So just like in the polynomial video, I'm going to draw a number line. On that number line, I'm going to mark my critical values. So start with -1, then 0, then positive 1. Now look, I've got 3 critical values, means I have 4 intervals. The first interval goes from -infinity to -1. I will test the -2 on that interval. The second interval goes from -1 to 0. I will test a -1/2 on that interval. The third interval goes from 0 to 1. I will test a positive 1/2. Okay, I could test anything between 0 and 1. It doesn't have to be a half. I could test 0.25 or a quarter if I want. And then the fourth interval goes from 1 all the way to the extreme right, or 1 to infinity. I will test a 2. You could test a 10, a 20, 100, a million, whatever you want. Something between 1 and infinity. Remember, you're testing the first derivative to find out if it's positive or negative. So when I plug a -2 in for x, think about what happens here. 2 times -2, the numerator would be a -4. Now the denominator, think about this. It doesn't matter what you do, what the inside the brackets works out to be, you're going to square it. So if this worked out to be a positive, you square it, you get a positive. If this works out to be a negative, you square it, you get a positive as well. So the denominator is always positive here, all right? So you'll have a -4 divided by a positive. Who cares what that works out to be? It's a negative divided by a positive. You know that the function is decreasing from -infinity to -1, okay? And just to prove that that would be a negative, if I filled the -2 in here and squared it, I'd get a 4. 1 minus 4 would be -3. -3 squared would be 9, positive 9. So I would have a -4 over a positive 9, which is a negative. Fill in a -1/2. This is a negative. This would be a positive. Okay, remember you're squaring this, so it's going to make it a positive. A negative divided by a positive is a negative. 1/2 goes in here. 2 times a half, that's 1. Positive. This will be a positive as well. A 2 times 2 is 4. Okay. 1 minus 4, 2 squared is 4. That's -3. -3 squared is 9. So you'd have 4 over 9. It's a positive. Okay, the numerator is a positive. The denominator is always a positive. So I could say it's increasing on, pick the intervals that have plus signs above them. So we could say 0 to 1 and 1 to infinity. Okay, from 0 to 1 and 1 to infinity. And it's also okay to say from 0 to infinity, but this is kind of nice because there's something happening at 1. And if you can remember, that was actually our vertical asymptote. And we would say it's decreasing on -infinity to -1 and -1 to 0. And again, you could go from -infinity to 0. Remember, -1 was also a vertical asymptote. So now I look at this and I'm examining the number line to see where it goes from negative to positive. Okay, well, it's negative on the left and right of -1, so that's neither a max or a min. This right here, this x value of 0, look, it's decreasing to the left of 0, it's coming down, and it's increasing to the right of 0, and it starts to go up. So it must reach a low point at 0. There's a local min at x equals 0. 1 would be neither because it's increasing to the right of 1 and increasing to the left of 1 and increasing to the right of 1. It doesn't change signs. So there's only a local minimum in this question. So there's a minimum at x equals 0. If I go back up here, okay, this is where we're at now. I'm going to find the local minimum. There is no max. The minimum value, I got to use f of x. Remember, I can determine from this number line that the minimum occurs when x is 0. So I'm going to fill a 0 in for x into the original to get the y value. We've done this calculation already. We end up with f at 0 equal to 0. 0 squared is 0. 1 minus 0 is 1. 0 divided by 1 is 0. So that minimum is the same as our x and y intercept. So really, we still only have this one point to sketch. Seems kind of odd, but that's fine. Next, we need to go with our intervals of concavity. Our intervals of concavity, all right, we're going to use the second derivative, so this right here, okay, which is just the derivative of this. And I showed the work on that a couple pages after this one. And then I'll find my inflection points by plugging the critical values back into the original. So, intervals of concavity, here we go. I want to get my critical values by taking the numerator and setting it equal to 0, but also by taking the denominator and setting it equal to 0. And I'm going to solve. So in this case, I would divide both sides by 2. Then I would subtract 3x squared from both sides, divide both sides by -3, and then I'll take the square root of both sides. Well, I can't take the square root of a -1/3. That means there is no critical value. This is impossible. I can't work that out. There is nothing, there's no value of x that's going to make that 0. Essentially what's happening, or what we can say, is the numerator is always positive. And if you think about that for a minute, check it out. Wouldn't matter what value of x you put in here, positive or negative. When you square it, you get a positive, and then you multiply it by +3, it stays positive. You add 1, it's positive. And you multiply by 2, it's always positive. So there is no critical value of the numerator. There's no value of x that makes that 0. The denominator, however, should work out no problem. Take the cubed root of both sides. The cubed root of 0 would be 0. Add x squared to both sides. Take the square root of both sides, and we get x equal to plus or minus 1. So my critical values are x equals -1 and +1. I am going to take and make a number line next to my second derivative. I will place the critical values, -1 and +1, on the number line. I will test my intervals from -∞ to -1. I'm going to test a -2. From -1 to +1, I am going to test a 0. From 1 to infinity, I'm going to test a +2. Now remember, you don't have to use the same test values as me, right? You just have to pick a number between -∞ and -1. Lots of options, folks. All right, from here, I'm plugging this test value into the second derivative. Well, we just finished saying that this numerator is always going to be positive. So let's just focus on this denominator. Okay, so right now, like if I fill a -2 into that second derivative, I'm going to have a positive over a, well, let's see. 1 minus -2 squared would be 4. 1 minus 4 is -3. -3 cubed is -27. I would have a positive over a negative, means that the function is concave down. The second derivative is negative from -infinity to -1. I'm going to fill a 0 in. Numerator's positive. Denominator would be 1 minus 0 squared. That's 1 minus 0, which is 1. 1 cubed is 1. It's a positive. Positive divided by a positive gives me a positive answer. So the second derivative is positive from -1 to +1, means it's concave up on that interval. And then I'm going to fill in a 2. Again, the numerator is a positive. Okay, 2 squared is 4, times 3 is 12, plus 1 is 13, times 2 is 26. 2 squared is 4, 1 minus 4 is -3, -3 cubed is -27. I have a positive divided by a negative. The second derivative would be a negative. All right. Concave down on the intervals with negative signs above them. So from -infinity to -1. And on the interval from 1 to infinity, okay? It is concave down on those two spots. It's concave up on this interval with the plus sign above it, from -1 to +1. Now it appears, remember from my notes, that if the second derivative changes signs at a critical value, so if it goes from negative to positive or from positive to negative, we have what we call an inflection point. All right, so it appears there's an inflection point at -1 and +1. Okay, some of you may remember that something else was happening at -1 and +1, but if you don't remember, you can try this. You can fill a -1 in for x and try and solve. And the math will show you that this works out to be 1 over 1 minus 1, or 1 over 0, which is undefined. Okay, it's actually going to either infinity or -infinity. That's what we'll check out in a minute here. When you have a number divided by 0, we have what we call an infinite discontinuity. Okay, and by a similar process over here, if I fill a +1 in, I get the same thing, 1 minus 1 squared. So 1, 1, 1. 1 squared is 1. 1 minus 1, we've got 1 over 0, which is undefined as well. And the reason that is, okay, the number line tells us that there are inflection points at -1 and +1. But the reason they're not is because we have vertical asymptotes there. All right, and that was what we did in step 3. So the vertical asymptotes actually create what we call an infinite discontinuity. Okay, so now it's time to sketch the curve. All right, so what you would do is, 1, locate all of your points. So the x-intercept was 0, 0. The y-intercept is also 0, 0. And the minimum value is 0, 0. That's the only point I know. There were no inflection points. Then I would place my vertical asymptotes. So what I'll do is I'll draw a vertical line at -1 and a vertical line at +1. these steer my curve. I'll also draw a horizontal line because there's a horizontal asymptote, oops, at -1. Where's my line gone? There it is. Okay, so there's my asymptotes. I'll make this full screen and stretch those vertical asymptotes out a little longer. Just a sec. And the same with this. Okay. Now, from our notes, we know that we cannot cut through a vertical asymptote. So this vertical asymptote is going to break the curve up into a left side and a right side. Same thing here. There'll be a piece of the curve in between here, and then there's going to be a piece of the curve to the right of this vertical asymptote. Now, in order to determine what's going on, I actually have to check the behavior near the vertical asymptote. I want to see what's happening to the left and to the right of -1, so that's this line. And I want to see what's happening to the left and right of 1. That's this line. So we're going to work with one-sided limits here. Now, this is the function, f of x, and I just wrote it in its factored form. So f of x was equal to x squared over 1 minus x squared, and then I factored it. I factored the denominator using a difference of squares. And I want to know what's happening on the left-hand side of -1. So I'm picking a value that is less than -1. So something like -1.1 or -1.01 or -1.001. If I plugged that in for x and I squared it, the numerator would be a positive. All right. This bracket down here on the bottom, 1 minus -1.1, well, that'll become 1 plus 1.1. It would give me 2.1. All right, and this factor down here, that would be 1 plus -1.1. That would give me a -0.1. It's a small negative. Smaller if I pick something like -1.01. Now, if you divide a positive by a positive times a negative, well, that would give me a negative. This would become positive times a negative. That means my y values, a positive divided by a negative, would get smaller, and they would actually approach -infinity. Okay, if I chose something even closer to -1, like -1.001 or -1.00001, this value would get infinitely small. It means my y values are getting really, really small. So what I can do is I'll actually draw this portion or this dot when x is -1.1, y is approaching -infinity. And how I would draw that on the curve is I would go just to the left of this line, -1, so -1.1, and my y values are getting infinitely small. So I'm going to go way down here. That looks like -5. I'm just going to stop there because I'm basically, if I went way down, I'd be off the grid. Okay, so I'm just going to the bottom of my graph. I'm going to do the same thing, but now I'm going to approach -1 from the right. So on this side of -1, the right of it, would be -0.9. Again, I'm checking to see what's happening to the y values. -0.9 squared, well, if you square a negative, you get a positive. 1 minus -0.9, that's 1 plus 0.9. This factor would become a positive. 1 plus 0.9, this factor, 1 plus -0.9, okay, that would be a positive 0.1. So you have a positive times a positive is a positive, then you have a positive divided by a positive would give you a positive. That means to the right of -1, so when x is -0.9, my y values are getting infinitely large. They're approaching positive infinity. Okay, so to draw that dot, I would go to the right of -1 when x is -0.9, and I would go to the top of my graph. Okay, And it wouldn't matter what the y scale was, I'd just go right to the top of it. Now I'm going to do the same thing for the left and right of 0.9. Remember, I'm plugging them into the original function. I want to see what's happening to the y values. So to the right of 1, sorry, to the left of 1, I'm using 0.9. If I square that, I get a positive. 1 minus 0.9, that would be a positive. And 1 plus 0.9, that would also be a positive as well. Okay, so 1 minus 0.9 is 0.1. 1 plus 0.9 is 1.9. 0.9 squared is 0.81. Positive, positive, positive. All the factors are positive, means my y values are going to approach a positive infinity. So again, keep in mind this is to the left of 1. Here's an x value of 1. To the left of it, I'm just on the inside of it. My y values are getting infinitely large, so I'm going to the top of my grid. And then finally, I'm going to do the same thing, but I'm approaching 1 from the right. So 1.1 is the number I chose, or you could use 1.01. If you square a 1.1, you get a positive 1.21. If you go 1.1 minus, sorry, 1 minus 1.1, scroll up, 1 minus 1.1, that gives me a negative 0.1. And if you went 1 plus 1.1, you'd get 2.1. Negative times a positive is a negative. A positive divided by a negative is a negative. My y values are getting infinitely small to the right. So to the right of 1, that would be just to the right of this green line, my y values are getting infinitely small. And from here, now I can do my intervals of increase and decrease. All right. I know that from negative infinity to negative 1, my function is decreasing. I also know that the further left I move, the closer I get to the horizontal asymptote of y equals negative 1. So this curve is going to bend up towards the horizontal asymptote. It's flattening out, and it bends down as it gets closer to negative 1. It's decreasing from negative 1 to 0, and then it's increasing. Try this again. This is tough. Bear with me. Not perfect. All right, it looks better on your Teams files. It's hard to do with my tablet here. Decreasing from negative 1 to 0, increasing from 0 to 1. Okay, it's also increasing from 1 to infinity. So I'm going to have this other branch that bends out this way. And that is what my curve would look like. It's also concave down from negative infinity to negative 1, concave up from negative 1 to 1, concave down from 1 to infinity. Another option here is to kind of just plug and play. Like if I want to know, some people have a hard time determining, well, am I above or below the horizontal asymptote here? And you can solve that pretty quick by like, let's examine this x value right here. You can just plug and play. If you fill a 5 in for x into the original, you could get the y value, and you end up with 25 over negative 24, which is a little less than negative 1. So you're on the underside of negative 1. Okay, so I just filled that 5 into the original equation, x squared over 1 minus x squared. 5 squared is 25. 1 minus 25 is negative 24. Okay, and that is an example of sketching a rational function. So plot your points. In this case, there was only the 1 point. And remember, this curve shouldn't be so wiggly or ragged in here. All right, it should be a nice, smooth, kind of like a parabolic shape to it. All right, in there. And then we have this branch here and a branch here. You cannot cut through a vertical asymptote. It's an infinite discontinuity. Notice we call it an infinite discontinuity because to the left, I'm going towards negative infinity. To the right, I'm going towards positive infinity. To the left of 1, I'm going to positive infinity. To the right of 1, I'm going to negative infinity. All right, I hope that helps. If you have any questions, fire away in the Teams app.